Okay, so here we are in question 1 of our Stats 1 paper. Now what I'm going to do is I'm just going to do this question for you, but I suspect many of you won't actually understand the reason for the formulas and why these things work. So if you stick around, what I'll do after is I'm going to try to justify what I'm doing and explain and elaborate the core principles, okay? Let's just do the question. So first, a summary of 50 values of x gives us sigma x minus q is equal to 700. And sigma x minus q squared is 14235, where q is a constant. We want to find the standard deviation of these values of x. Now, the key idea here is to realize that the variance of x minus q is actually the same thing as the variance of x. Okay, now, what that means there is that if I take all of my values, right? So all of my x values, and I add or subtract a constant from all of them, then the variance isn't actually going to change. Okay, there's going to be no change of variance caused by adding or subtracting a constant. So being asked to find the variance of x is the same thing as being asked to find the variance of this. Well, then the second thing we need to know is the formula for the variance. And the formula for the variance of x is equal to sigma x squared upon n minus sigma x upon n all squared. So if that's the case, well, what's the variance of x minus q? Well, the variance of x minus q is going to be equal to sigma x minus q all squared upon n minus sigma x upon n, right, sigma x minus q upon n all squared. Okay, so in other words, instead of finding the variance of x, finding the variance of x minus q just means we replace the x in our formula with x minus q. Okay, so that's what we've done there and there. Well, we know the summation of x minus q squared because we're given it in the question. It's 14235. So we've got 14235 divided by 50. And we also know the summation of x minus q, that's 700. So here we've got 700 upon 50 all squared. So then the issue just becomes typing these numbers into a calculator, which is exactly what I'm going to do. So I will do 700 divided by 50, okay, all squared. Now we'll do 14235 divided by 50, and then minus that answer there. And I get 887 upon 10 is 88.7. Now, remember what I said at the beginning, that the variance of x minus q is the same thing as the variance of x. So I can automatically state that this thing is actually just the variance of x. And then we need to remember from then that the standard deviation is the square root of the variance. So the standard deviation sigma is just the square root of 88.7. And so what I get there is 9.418. Okay, so 9.42. And I just want to double check because I sometimes forget what the level of accuracy is on the stats exams. Let me just check that again. 9.42. Yeah, okay. So 3 significant figures. All right. Okay, then let's have a look at part 2. So given that sigma x is equal to 2865, I want to find the value of q. Okay, then. Well, again, we've got to try to understand a principle here. Let's say we've got sigma x plus a. And what's unwritten here is actually how many times we're adding this up. So I will write down here what is implied, which is we're adding up from a value of I is 1 all the way up to a value of I, which is n. So really, strictly speaking, we should call this xi plus a, summed from I is 1 to I is n. Well, if we do that, what we've got to understand is this is x1 plus a plus x2 plus a plus x3 plus a all the way up to xn plus a. Okay, and if you do that, well, what are you really doing? You're adding up x1, x2, x3, x4 all the way up to xn. So that's actually the same thing as sigma xi from I is equal to 1 to n. And then what are you doing? Well, you're doing a plus a plus a plus a plus a n times, so that's n lots of a. So way you could write this is to say the sigma x plus a is actually the same thing as sigma x plus n times by a. And that's really the key principle that we've got to use here. So sigma x plus a, we are told in the question, sigma x minus q is equal to 700. So let's just change this. So now what we're doing is sigma x minus q. What I'm trying to say is that's the same thing as sigma x plus n times by negative q. And we know that sigma x minus q is 700. We're told that sigma x is 2865, so 2865. And we're told that n is 50, so minus 50q. Funny looking q that. Okay, so I've just got to rearrange it. So what should I do? Well, I will do 2865 minus 700. Okay, so I brought the 700 to the right, bring the 50q to the left, divide by 50. Q is equal to 433 upon 10, which is 43.3. So Q is equal to 43.3. Okay, and that should be our answer. Okay, so we're going to try to explain this formula here for the variance today. We want to try to explain where it comes from and what it's telling us. And I think probably the best way to do that is we are going to start with some data, a very simple data, in order to illustrate this point. So let's have the points 1, 2, 4, and 5. And the first thing we're going to do is we're going to calculate the mean of those points of data. And the mean is given by this formula here, sigma x over n. Now, sigma x means we add up all of these data points. We add up 1 plus 2 plus 4 plus 5. And then we're going to divide through the total number of data, which in this case is 4. So if I do 1 plus 2 plus 4 plus 5, I get 12. And if I do 12 divided by 4, I'm going to get 3. So the mean of this data is 3. Now, it's important to understand at this point what the mean is trying to tell us. The mean is what we call a measure of central tendency. That is a fancy way of saying the mean is telling us where we think the center is. Now, there's no one single way in which we can define the center of a piece of data. We could use the mode, we could use the median to name a couple other examples, but the mean is this particular way. We're going to add up all of our values. We're going to divide by the total number of values. Now, how does that help us when it comes to the concept of the variance? Well, the variance is a measure of the spread of the data, right? In other words, how far it is distributed away from this central point here, this central point of 3. So the way we could do that is we could take the distance of each of these points, 1, 2, 4, and 5, and measure its distance away from 3 there. So let's try to do that. Take the distance by doing each of the x coordinates minus the mean, minus this. So we do 1 minus 3, we're going to get negative 2. 2 minus 3, we get negative 1. 4 minus 3, we get positive 1. And 5 minus 3, we get positive 2. And so we can say, okay, well, we can measure the spread of this data by taking the mean of each of these distances, right? So that would mean that we would add up all of these distances, right? And then divide by 4. But if we do that, we're going to end up with a problem, right? If we say that we add up all the distances and divide by the total number of data points, then we're going to get negative 2 plus negative 1 plus positive 1 plus positive 2 is equal to 0. And in that case, that means that we're going to say that our spread is going to be equal to 0. And that's clearly nonsense, right? That can't be right. And the reason we get that is because we've got these negative values here. So what we want to do is we want to get rid of these negative values so we can kind of turn them into positives. And the simplest way to do that is just to square them. Right, so if I square each of these values, I'm going to get 4, 1, 1, and 4. So now what we're going to do is we're going to say, okay, a way of measuring our spread, right, how far each data point is away from the middle, is to say we are going to do the mean of the distance squared. Right? So we're going to do the mean of the distance squared. In other words, what we're going to do is we're going to add up all of these values here and then divide through by the number of values 4. Now that is what we refer to as the variance, right? The variance is the mean of the distance squareds. So in this particular case, what I'm going to do is I'm going to get 4 plus 1 plus 1 plus 4, all divided through by 4, which is 10 upon 4, and that's 5 upon 2. But what we've got here is we've got a variance of our data is 5 upon 2. Well, what I want to do is I want to take that formula there, right, the mean of the distances squared, and try to rework it a little bit. So I'm just going to go down. All right, our standard deviation is our mean of the distances squared. But what is our distance squared? Well, we said that that was the x value minus the mean all squared, right? So in other words, we replace d with x minus the mean. Well, we can then expand this thing here. We expand that bracket. What we'll get if we do that is the summation of x squared minus 2 mu x plus mu squared. And this is all divided through by n. Well, now this thing can actually be split up, right? So we can split up our summation. This is going to be the same thing as the summation of x squared over n minus the summation of 2 mu x over n. Do that a bit better, sorry. Plus the summation of mu squared upon n. Now, there are a couple of things to realize here about summations. Now, the first of that is that this thing here, the 2 mu, that's a constant. We can pull it out of the summation. So let's do that. This is going to be the summation of x squared upon n minus 2 mu times by the summation of x upon n. And then what's going on here? Well, if we've got the summation of mu squared, now mu squared is just a constant. So this summation of mu squared means we're going to do mu squared plus mu squared plus mu squared plus mu squared. We're going to do it n times. So what we're going to end up with there is n lots of mu squared, all divided through by n. Okay, so it's looking a little bit complicated so far, but it is going to simplify. How is it going to simplify? Well, we previously defined the mean, that is mu, as being sigma x upon n. Right, so I can replace this mu here with sigma x upon n. Do that, sigma x upon n times by sigma x upon n. Right, so in other words, I've replaced that mu there with that thing there. I've replaced this thing here with that thing there. Okay? And then if I've got n divided by n, that cancels off, and I'm left with mu squared, and I've just said that mu squared is sigma x upon n, all squared, right? So I replace the mu with sigma x upon n. Well, now if we just think about it, this thing is sigma x upon n times by sigma x upon n. Well, that's the same thing as sigma x upon n squared. So I can sort of get rid of this thing like that and replace it with that. So I've got, in summary, sigma x squared upon n minus 2 lots of sigma x upon n squared plus sigma x upon n squared. Well, if I've got minus 2 plus 1, I end up with minus sigma x upon n squared. And that's why we end up with the formula for the variance that you're mostly familiar with, the summation of the x squareds divided by n minus basically the mean, sigma x upon n squared. Okay, so that's where the formula is coming from. But what I hope you see is basically the core idea of the variance, right? The variance is saying, let's find the mean of the distance squareds, right? That's what that thing is, right? We take each of the distances from the middle, from our mean, we square them to get these, and then we find the mean of these values here, right? And what that's telling us is giving us a description of how spread out the data is. Okay, so mean is a measure of central tendency. It's a measure of where the middle is. And the variance, this thing, which is the mean of the distances squared, is a measure of the spread of the data. In other words, how far the data is spread out from that central value in the middle. Okay, I hope that was helpful, guys. See you next time. Okay, let's say we've got two sets of data. We've got x, which are the data points 1, 2, 4, and 5. And we've got y, which is the same as x, but each data point we've added 10 to it. So instead of 1, we've got 11, instead of 2, we've got 12, instead of 4, we've got 14, instead of 5, we've got 15. Well, what we want to try to think through is what is the relationship between the mean and the variance of this data and the mean and the variance of this data. Okay, well, let's go back to our definition of the mean. Our definition of the mean is that we add up all of our values and divide by the total number of values. So the mean of the x distribution means we've got to add up 1 plus 2 plus 4 plus 5 and divide through by 4. So let's do that. This is 1 plus 2 plus 4 plus 5, all divided through by 4. If we do that, we're going to get 12 divided by 4, which is 3. Okay, so we've done that. Now, we can do the same thing, but for our y distribution, we can add up all of our y values and divide through by 4. But remember, actually, our y's can be defined as our x values plus 10. So this is the same thing as doing the summation of our x values plus 10 divided by, in this case, n, which is 4. Well, if we do this, if we write this out, then what's this going to be the same as? This is going to be the same as 1 plus 10 plus 2 plus 10 plus 4 plus 10. Sorry, better get rid of that. Plus 4 plus 10 plus 5 plus 10. Okay, all divided through by 4. Well, I can rearrange that, right? I can rewrite this as 1 plus 2 plus 4 plus 5, that's one thing, plus 10 plus 10 plus 10 plus 10. In other words, I've got 4 10s to add up, which is 4 times by 10. All divided through by 4. Now the question is, guys, what is this 1 plus 2 plus 4 plus 5? That's the same thing as our sigma x, right? The summation of our x's here. I can rewrite this thing as sigma x. So let's do that. This is sigma x plus 4 times by 10 over 4. Well, then I can split this up. Say this is sigma x upon 4 plus 4 times by 10 divided by 4, which is just 10. Now, what is our sigma x upon 4? If we go back, remember, this is just the mean of x, right? So this is the same thing as mu x. What we end up with here is that the mean for y is the same thing as the mean for x plus 10. Right? So in other words, if we were to go back to our data points here, right, the mean for x that we defined earlier, that thing was 3, right? So the mean of that was 3. So how can we go to the mean for y? Well, the mean for y will be 3 plus 10, which is 13. Okay, so if we've got a distribution of x, we take that distribution, we add some constant value to it, so we can add 10 or 11 or 12 or 13 or whatever it is, then the mean is going to shift by the same amount, right? We take our mean, in this case, we add 10, all right? So to summarize that, we can say that if, let's say y is equal to x plus some constant k, then the mean of y is going to be the same thing as the mean of x, but just plus that constant k. All right, so we've done the mean. What about the variance? Well, let's go back up again. Now, in an earlier video, I defined the variance in a distinctive way. You're used to using the formula sigma x squared upon n minus sigma x upon n all squared. What I said is that the variance is really the mean of the distance squared from the center. So we write that down. Sorry about that. Understanding the variance of x, for example, is the summation of our x points from our mean, all squared, divided through by n. So then what would be our variance for y? Our variance for y is going to be the summation of our y coordinates minus the mean of y, all squared, upon n. Well, we've already defined what y is in this particular case. Our y is x plus 10, and our mean was our mean of x plus 10, because that's the result that we've just got. So this thing is going to simplify, and it should simplify quite nicely. Our n is 4 in this case, because we're going to have on the inside of this 10 minus 10. So what are we actually going to end up with here? If we simplify, we're going to get the summation of x minus mu x all squared upon 4. And so what is this the same thing as? Well, this is the same thing as the variance of x. In other words, what we've shown is that the variance of y is the same thing as the variance of x. Now, this should kind of make some intuitive sense, because if you go back up and you look at the data, and you ask yourself, what does variance tell us? Variance tells us the spread of the data from the central point. Well, if I add 10 to each of these data points, okay, then what happens is the middle of that data also shifts up by 10, right? So the middle shifts up by 10. But the spread of the data remains the same, right? In other words, the way in which these x values are spread apart from the center is going to be exactly the same as the way these y values are spread apart from that data, right? Because if you take a whole, all your piece of data and you add the same value to them, then they're all going to move by the same distance, which means that they're not going to get any more spread apart and they're not going to get any closer. They're all going to have the same distance with respect to each other. So that means that your variance here is going to be the same. So to summarize, we have said that if we add a constant to all of our variables, then the mean also moves up by that constant. And we can now also further clarify that and say the variance doesn't change, right? So the variance of y will be the same as the variance of x. Okay, I hope that was helpful. Okay, so we're in question 3. It's a combinations permutation style question. We want to find the number of ways in which a committee of 6 people can be chosen from 6 men and 8 women if it must include 3 men and 3 women. Well, I think the first thing with these questions is we need to answer the question, are we in permutations or are we in combinations? And the key distinction between these two is that for permutations, order matters. Combinations, order does not matter. Now, what do I mean by that? I think the simplest thing to think about is a password. So let's say we've got a password and the letters of the password are red, for example, R-E-D. If that's our password, then not only do we need to have the letters R, E, and D, but we need to have them in that order. In other words, we can't have the same letters, but in a different order, such as D, R, E, right? This is considered to be a different thing to this. So if we've got a situation in which order matters, such as a password, then we need to use permutations. But if we're in a situation where order does not matter, then we need to use combinations. And that's the situation here, right? Because if we've got, if we're choosing a committee of 6 people, let's say we wanted to choose 4 people, right? John, Paul, George, and Ringo, then that would be the same thing as choosing Ringo, Paul, George, and John, or John, Ringo, George, and Paul, or Paul, Ringo, John, George, right? It doesn't matter, in other words, in which order I choose the people or how they're arranged. So long as I got the same 4 people, then it's considered to be the same thing. So in this particular case, it doesn't matter at all the order in which I select these 6 people, so long as I've got that particular group of 6. And so therefore, in this particular case, we've got combinations. Now then, let's try to think how to do this. We want to choose such we've got 3 men and 3 women. Well, how many ways can we choose 3 men from 6 men? Well, that is going to be 6C3. That's the number of ways we can choose 3 men from 6 men. Then how many ways can we choose 3 women from 8 women? Well, that is going to be 8C3. So then the question becomes, well, are we going to be adding these two things or are we going to be multiplying them? Short way to remember this is that if we have got and, then we multiply. If we've got or, then we add. What do I mean by this? We need to have 3 men and 3 women at the same time. That means in this case, we're going to be multiplying. We add up when we've got the situation where we've got one case or another case, right? We need to consider 2 or 3 cases separately, in which case then we add. But in this case, what we're saying is we want to have this thing, the 3 men, and also this thing, the 3 women at the same time. Therefore, we are multiplying. So all I'm going to do is I'm just going to put that into my calculator. So 6C3 times by 8C3, and that gives me 1120. So 1120. Okay, then let's go to part B. A different committee of 6 people is to be chosen from 6 men and 8 women. 3 of the 6 men are brothers. I want to find the number of ways in which this committee can be chosen if there are no restrictions on the number of men and women. In other words, actually, we can basically treat these as being 14 people. Okay, so I treat this not as 6 men and 8 women anymore, but just 14 people. And it must include no more than 2 of the brothers, right? So no more than 2 of the brothers. So what we've got here is we've got a couple of different cases to consider, right? We can either have, we've got 0 brothers, or we can have 1 brother, or we can have 2 brothers. What we cannot have is we cannot have 3 brothers. So let's do this in the slow method first, and I'm going to show you a way to do it a bit faster, but we're going to consider this. So how many ways can I choose if there are 0 brothers? Well, that means that I've got to choose 6 people, but I can only choose from 11. Why can I only choose from 11? Because instead of having 14 people to choose from, I can no longer choose 3 of those people because they're the 3 brothers. So actually, I've got 11 people to choose from here. And what I'm doing is I'm choosing 6 of them. Okay, so this is going to be 11C6. Okay, well, now let's consider the other case. What I've got is I've got 1 brother. Okay, well, how many ways can I choose 1 brother out of 3 brothers? Well, there are 3 ways to do that, but if you want to write it more precisely, it's 3C1, right? Because there are 3 brothers, and I'm choosing 1 of those brothers. And then that means the remaining 5 people that I've got to choose for my committee have got to come from 11 people here, because I can't choose the brothers, right? So I've got to consider that there are 11 people here who are not the brothers, and I'm choosing now 5 of them, so that's going to be 11C5. And again, what I'm going to do is I'm going to multiply these because I want the 1 brother and the 5 other people at the same time. Okay, now then, in the last case, if I've got 2 brothers, then I've got to ask how many ways can I choose 2 brothers from 3? That's 3C2. Okay, and then what have I got left remaining? Well, I've got to choose 4 people, and I've got to choose 4 people from 11 people, right? Because it's 11 people who are the people that are not the brothers. We've got 11C4, and again, I'm multiplying these because I want the 2 brothers and the 4 other people. So now what I'm going to do is I'm going to just multiply all these. Okay, so I got 11C6, so 11C6 is 462. And I've got 3C1 times by 11C5 is 1386. And I've got 3C2 times by 11C4 is 990. So these are the 3 different ways that I can have an outcome that I want. So I can either be this way, or this way, or this way. And what I said in part A is that when we've got something and something, then we need to multiply. If we've got something or something, then we need to add, right? So because we can either have 0 brothers or 1 brother or 2 brothers, then in this case, what we need to do is we need to add up all of these outcomes because these are 3 separate cases. So we're going to do 462, right? So 462 plus 1386 plus 990. And that's going to give me 2838. So 2838 should be my answer. Now, that's quite a slow way of doing it. So I think let's try to do it a little bit faster because really what we've got is we've got a third option to consider, right? The third option is sort of, what if we had the three brothers all together? Now, the way in which we can choose three brothers is 3C3, which is just one. And then the way we can choose the remaining is going to be 11C3, because we've got 11 people to choose from. We're choosing 3. So what we're going to get there is 11C3. And that is equal to 165. Now, if you think about it, what this represents is the number of ways in which I cannot select my committee, right? So I can't have this outcome. So 165 is the number of ways in which I cannot select my particular committee. Well, if there were no restrictions, right, what would be the total number of ways? No restrictions. What would be the total number of ways? Well, I've got 14 people in total, and I can choose 6 of them. So I've got 14C6. So if I do that, 14C6, that's equal to 3003. Okay. So then the number of ways in which I can have either 0 brothers, 1 brother, or 2 brothers is to take this thing and subtract that thing, right? Because I'm taking away the thing that I cannot have. So if I do 3003 minus 165, then that's going to be equal to minus 165. That's equal to 2838. And what do you notice? This number is the same as the other number. So what we've done is we've done the question in 2 different ways. And we've got the same result, which is hopefully quite reassuring for you. Now, I think it seems to be the case that the second way I did it is obviously much faster. But I think it's helpful for you as well to be able to think through the way I did it in the first case, which is to be nice and systematic. So I think you want to aim to be able to do it in both ways, if only because actually if you do it both ways and you get the same answer, that reinforces your confidence that you are right. Okay, hope that was helpful. Okay, so here we are in question 3. We want to find the number of different arrangements of the 8 letters in the word cocooned. Well, we're told in the question that there are 8 letters. Okay, and then what we've got to do is we've got to calculate the number of letters that are repeated. So we've got 2 C's there, right? So I'm going to write down we've got 2 C's repeated. And we've got 3 O's repeated, right? So 1, 2, 3 O's. And there are no other letters repeated. Now, the way in which we find the number of ways, therefore, so the number of ways is going to be the number of letters factorial, so it's going to be 8 factorial, divided by the number of repeated letters factorial. So we're going to have 2 factorial for the 2 C's. We're going to have 3 factorial for the 3 O's. So we just put that into our calculator. We're going to get 8 factorial divided by 2 factorial, and again divided by 3 factorial. So we get 3360 is the total number of ways. Now, if you're not sure why we do this, I'm going to try to do another video where I'm going to explain that. But the key thing you just need to know is you take the number of letters in total, and you do that factorial on the numerator, and you take the number of repeated letters and you count them, so you get 2 C's, 3 O's, and you put that on the denominator, 2 factorial, 3 factorial. Okay, let's have a look at B. We want to find the number of different arrangements of the 8 letters in the word cocooned in which the first letter is O, the last letter is N. Well, we just draw this out, I think, is the best way to do it. So 1, 2, 3, 4, 5, 6, 7, 8. And what we're saying is first letter's got to be O, second letter's got to be N. So really what we're doing is we are just arranging the middle 6 letters where we have excluded an O and an N. So what we're really trying to do here is find the number of ways in which we can arrange the remaining letters CO, CO, and ED. Well, if we think about that, how many letters have we got to arrange? We've got 6 letters in this particular case, right? Because we've excluded 2. Got 6 letters. And how many of them are repeated? Well, we've got 2 C's and we've got 2 O's. So the number of ways in this case is going to be equal to 6 factorial over 2 factorial, 2 factorial. If I do that on my calculator, I get 6 factorial divided by 2 factorial, 2 factorial is going to give me 180. So there are 180 ways. Okay. All right. Let's do C. I want to find the probability that a randomly chosen arrangement of the 8 letters in the word cocooned has all 3 O's together, given that the 2 C's are next to each other. So what we got here is actually we've got conditional probability. We've got a given that. I think a helpful thing to do is actually to define the event. So I'm going to define event A as the 3 O's are together. Okay, and I'm going to define event B as being the 2 C's are together. So if that's the case, what we're being asked to do is we're being asked to find the probability of A given B, right? We want the probability that the three O's are together given that the two C's are together. And the probability of A given B is the probability of A intersection B divided by the probability of B. And so what we need to do is we need to consider these two cases, the case A intersection B and the case just B on its own. Well, A intersection B, we're going to have the three O's together and the two C's together at the same time. So 1, 2, 3, 4, 5, 6, 7, 8. Let's say this is the three O's together. So those are our O's. And these things are our two C's together. So those are our C's. What are we going to have? Well, we have like one item here, another item, and then three more items, right? Three other letters. So we can count this as 1, 2, 3, 4, 5 different objects. How many ways can we rearrange the 5 objects? So the number of ways is going to be 5 factorial. Number of ways is equal to 5 factorial. And you may be asking, well, hang on, don't we need to count the number of arrangements of the O's and the number of arrangements of the C's? Wouldn't that be 3 factorial there? And wouldn't that be 2 factorial there? Well, okay, but these are all the same thing, right? It doesn't matter how I rearrange the O's. I'm always going to get the same thing in the end. So I could say, okay, well, I've got 3 factorial ways of arranging them. But because they're all identical, I'd have to divide by 3 factorial anyway, right? So in the end, it doesn't make any difference. So I can just treat this as just like one thing, basically. Okay, what about the probability of B? Well, B, in this particular case, what we've got is the two C's are together, isn't it? That's the two C's. So let's draw it out again. So 1, 2, 3, 4, 5, 6, 7, 8. And let's say our two C's are together. So that's like that. Okay. Well, how many ways can I arrange that? In this particular case, what I've got is I've got one item, 2, 3, 4, 5, 6, 7 items, right? So one item plus a remaining 1, 2, 3, 4, 5, 6. So 7 items in total. But of these remaining items, I've got 3 O's which are repeated. So what I need to do is I say, okay, I've got the number of ways here. Number of ways is equal to 7 factorial divided by 3 factorial. Okay, now obviously the probability of A intersection B is going to be this number of ways 5 factorial divided by the total number of ways which we calculated earlier. And the probability of B is going to be this number of ways divided by the total number of ways which we calculated earlier. But it really doesn't matter, because when we get to the end, we say, okay, what we want is the probability of A given B. We can just do the number of ways in which we can do A and B, which is 5 factorial, over the number of ways in which we can do B, which is 7 factorial, divided by 3 factorial. What I'm going to do is I'm just going to calculate that. So we've got 5 factorial on the top. That's 120. Okay, and we got 7 factorial divided by 3 factorial on the bottom, which is 840. So 120 divided by 840 is 1 upon 7. So the probability of A given B is 1 upon 7. All right, so here we are in question 4. We got a mathematical puzzle given to a large number of students. The time taken to complete the puzzle are normally distributed with a mean of 14.6 minutes and a standard deviation of 5.2 minutes. So we can probably write this down, right? Let X be time taken to complete puzzle. Sorry about the handwriting. And so therefore what we're saying is that X is normally distributed with a mean of 14.6 and with a standard deviation of 5.2, so variance 5.2 squared, okay? I know it seems a little bit tedious to write this out, but it is good practice to define what your variable is and to state your distribution like that. Okay, part A. In a random sample of 250 of the students, how many would you expect to have taken more than 20 minutes to complete the puzzle? In other words, what we're being asked to find really is the probability of taking longer than 20 minutes to complete the puzzle. So we want to find the probability that X is greater than or equal to 20. Well, then we can convert this to the Z distribution using the formula, I guess. Z is equal to X minus mu upon sigma. So instead of calculating the probability that X is greater than 20, we consider calculating the probability that Z is greater than 20 minus 14.6, all divided through by 5.2. So that's the probability Z is greater than. Let me just use my calculator. So 20 minus 14.6, okay, and then divided by 5.2. You know, there's 27 upon 26, and we get that as a decimal. That's 1.03846. Okay, so I'll put it to 4 decimal places. Now, the problem is with our tables of data that you're given in your exam booklet is that you only have got the probability that Z is less than a certain value. You don't have the probability that Z is greater than a certain value. So we need to understand how to manipulate our data. So let's imagine that what we've got here is we've got our Z distribution. So the Z distribution is symmetrical about 0, and it looks something like this. Okay, it's a nice bell curve. Oh, that's going to be symmetrical. Sorry, that's a bit rubbish. Okay. Now we're being asked to find the probability that Z is greater than 1.0385. So let's indicate that here. So let's say that's our value, 1.0385. And we're being asked to find this region here, right? This probability. Okay, that's the thing that we're being asked to find. But this is going to be the same thing as 1 minus this probability here, right? That probability, that in green, right? Because the area underneath the whole curve must be 1, because the sum of the probabilities must be 1. So if we want to find the red region, what we can do is we can find 1 minus the green region. So in other words, what we can say is that this probability is going to be the same as 1 minus the probability that Z is less than 1.0385. And we are able to use our data to find this value. So we want to find 1.0385 on our table of data. So let's go over here. So Z is 1, that's there, 1.03, so that's going to be there. So that's 0.8485. It's 1.038, isn't it? So we got to add, is it 19 there? I just want to double check my numbers. 1.038. So 1.03, that's that thing there. Let me just highlight that. 1.03, that thing. And then 8 is going to be that there. So what I need to do is I need to take the value 0.8485 and add on to it the 0.0019. If I do that, what I get is 0.08485. Sorry, 0.8485 is what I meant to say, plus 0.0019. And what I get is 0.8504. So 0.8504. So what I need to do is I need to calculate this is 1 minus 0.8504. And 1 minus that is going to be 0.1496. So that's equal to 0.1496. That's the probability that a student takes more than 20 minutes to complete the test. But we weren't asked to do that, remember? The actual question is, how many out of the 250 would I expect to have taken more than 20 minutes? So what I've got to do is I've got to take that probability and times it by 250. So 250 students times by the probability that each student takes more than 20 minutes, which is that. If I do that times by 250, what I'm going to get is 37.4. And of course, can you have 37.4 students, right? Is that a possible thing? And the answer to that is no. So what we need to do is we need to round this. Now, the mark scheme, it says you can have 37 or 34, right? I mean, yeah, not great. I would round down, but either is acceptable. Okay, so basically we take our probability that we are greater than 20 minutes, we times by the total number, and then what we got to do is we got to leave this as an integer value because we need to recognize that we can only have integer values of students. Okay. Okay, so we got the next part of this question. All the students are given a second puzzle to complete. Their times in minutes are normally distributed with a mean of mu and the standard deviation sigma. It is found that 20% of students have times less than 14.5 minutes and 67% of students have times greater than 18.5 minutes. I want to find the value of mu and the value of sigma. Well, I think it's probably helpful again in this case. We're just going to define our distribution. So we're going to say let y be the time taken on the second puzzle. We want to distinguish this from what we've done in part A. And so therefore we know that y is normally distributed with some unknown mean and some unknown variance. Okay, then what we should do, I think, next is we want to say, want to find the probability, or sorry, we've got two bits of information rather. The probability that y is less than 14.5 is equal to 20% or 0.2. And we've also got the probability that y is greater than 18.5 is equal to 67% or 0.67. Okay, now I think it's helpful to think about these in terms of the Z distribution first. So what we're going to do is we're going to transfer these to the Z distribution. Okay, so we are finding the probability that Z is less than some particular value. I'll call that Z1 being equal to 0.2. And the probability that Z is greater than some other value, Z2, and that's going to be equal to 0.67. Okay, so we want to convert our problem into the Z domain because then we've got the tables of data that enable us to do that. So what we want to do is we want to try to find this value of Z1 and this value of Z2 here because it's going to correspond to the 14.5 and the 18.5 there. So let's focus on the first one. The probability that Z is less than Z1 being equal to 0.2. Well, probably a good idea just to draw out what our distribution looks like, right? So let's draw out the Z distribution. Okay, like that. And it's going to be centered on the point Z is 0. And we've got a curve that looks roughly like that. Okay, so I'll draw that out. And that. And if we've got a probability that we're less than Z1 being 0.2, then Z1 we're saying is kind of like here. And that will be this region. Okay, so let me just try to highlight that. We're talking about that region there. So this probability, right, corresponds to that region. Now, unfortunately, that means that that value of Z1 is going to be negative, isn't it? And we don't have negative values of Z1 on our tables of data. So we need to use the properties of symmetry. And the properties of symmetry is going to say, okay, well, that little green region there is going to be the same thing as this green region here. Okay, because it's symmetrical about the z-axis, right? Or rather about the y-axis in this case, kind of this thing here. So what's this Z1 value going to be? This Z value is going to be minus Z1. Because if you think about it, if this thing is whatever, minus 0.8 or whatever it is, then this thing is going to be minus 0.8, which is going to be plus 0.8. So my whole point is that this probability here is the same as this probability. So what we can say is, all right, the probability that Z is less than Z1 has got to be the same thing as the probability that Z is greater than negative Z1. And we don't have the probabilities that Z is greater. What we have is the probabilities that Z is less. We're going to change this, say this is the same thing as 1 minus the probability that Z is less than negative Z1. Okay, so I hope that makes sense there. In other words, since the tables of data don't allow us to calculate this region being greater than, what we've got to do is kind of got to calculate that region there, or look at that region and say what we're dealing is 1 minus that. So if this thing here is equal to 0.2, we've got 0.2 is equal to 1 minus the probability that Z is less than minus Z1, which is the same thing as finding the probability that Z is less than negative Z1 being equal to 0.8. So now what I got to do is I've got to try to find 0.8 on my table of data. So let's go over here. Let's find 0.8. So 0.8, where is that going to be? Going to be somewhere. There we've got 0.8 here, 0.79, 0.7. Okay, now look, here we go from 0.7995 to 0.8023. Let me try to zoom in that a little bit more so you can see a bit better. Okay, so we're either side of 0.8 here. Now, what can we do? We can take that value, this thing here, 0.7995, and ideally what we want to do is want to add 0.0005, which is want to add that value there. So what Z value gives us that? Well, the Z value's got to be 0.842, right? So 0.842. So Z1, or our negative Z1 rather, go down here, zoom that out. Say therefore, our negative Z1 is equal to 0.842. Just confirm that, 0.842, yeah. Okay, and if that's the case, then the Z1 that we're interested in is equal to minus 0.842. So we got that value there. All right, then what we want to do is want to get the next value, don't we? So we are interested now in the probability that Z is greater than Z2 is equal to 0.67. So let me just get rid of these things on our diagrams. Let's get rid of that, that. And so now what we're interested in is the probability that Z is greater than Z2 is equal to 0.67. Well, what's that going to look like? That's going to look roughly like this. So let's say here's our Z2. Okay, well, the probability of being greater than Z2 is equal to 0.67. That's going to look something like this, that region there. But again, what's going to happen is that Z2 value is going to be negative, isn't it? Because it's on the left-hand side. We don't have negative values with Z. So what we've got to do is we've got to do a little bit of symmetry. And we've got to take this symmetrical value here, which is going to be negative Z2. I put the negative because it kind of flips the sign. And so what we're going to calculate is the probability that we're on the left of that, because that's the same thing as the probability of being on the right of that. So if I go over here, what I'm trying to say now is that the probability that Z is greater than Z2 being equal to 0.67 is the same thing as the probability of Z being less than minus Z2 being equal to 0.67, right? We just use the property of symmetry that we've just seen. So what I want to do is I want to go to my table of data again. I want to find out where 0.67 is. Oh, so let's try to zoom in. 0.67. Now, if I find 0.67, that is exactly there. There's that thing. Let's highlight that. That's 0.67. So that's a Z value of 0.44. So I'm going to go over here. I'm going to say, okay, well, that Z value is 0.44. Write that down. So negative Z2 is equal to 0.44. And so Z2 is equal to minus 0.44. Okay, so let's recap now. We've calculated our two Z values, and they're going to correspond to these values here. So, right, our 1.45 corresponds to a Z value of negative 0.842, and this value here, 18.5, corresponds to a Z value of negative 0.44. So what are we going to do? Well, we've got to use our formula. So we know that Z is equal to X minus mu upon sigma, or in this case, Y minus mu upon sigma. And we can rearrange this to say Y is equal to Z sigma plus mu. Okay, so what we're going to do is just going to substitute our two values in as we did. So our first Y value was 14.5. So we're going to say 14.5 is equal to the Z value times by sigma. So the Z value we had was negative 0.842. So negative negative 0.842, I think that's right, times by sigma plus mu. And the second equation we've got, our y value is 18.5. So here what we've got is we've got 18.5 is equal to our z value, which was negative 0.44, if I remember right, negative 0.44 times by sigma plus mu. Let me just confirm that. Yeah, it was right. So what's this thing? Well, what we've got here is we just basically got simultaneous equations. So we need to be able to solve these. And the easiest way to solve them is to do a subtraction, right? If I subtract one equation from the other, like that, then the m's are going to cancel off. So let me do that. I'm going to have 14.5 minus 18.5, and that's going to give me negative 4. So I got negative 4 here is equal to, so I got to be very careful, minus 0.842 minus, that's going to be plus 0.44. And that gives me a value of negative 0.402 sigma. And again, the mu's disappear. But if I do that, then sigma is going to be negative 4 divided by our answer. And that gives me a sigma of 9.95. Okay. I'm just going to quickly check the mark scheme, see if I'm on the right track. Yeah, sigma is 9.95. Okay, jolly good. So now that I've got sigma, I can just substitute in to find mu. So I can say, all right, 14.5 is equal to, actually, I'll use 18.5. Use the other one. So 18.5 is equal to minus 0.44 times by 9.95, which we just calculated, plus mu. Let me do that. So times by 0.44. Okay. Get that. I'm going to plus it to 18.5. Like that. And that gives me a value of 22.87. And I'm just going to check the answer to make sure I'm right. Yeah, okay, I've checked. So it's 22.9 according to the mark scheme. So mu is equal to 22.9. All right, now, look, these questions take a little bit of a while, but they're fairly standard questions. So hopefully, as you're getting ready for your exam, you should have practiced this kind of thing several times. Now, the really confusing thing here, I think, is finding what the Z scores are, right? The simultaneous equations at the end is hopefully quite easy, but finding the Z scores is difficult. And what I strongly recommend you do is firstly, you say, I'm not even going to think about this as a problem with Y. I'm going to change this immediately to a problem with Z, where I've got these unknown Z values that I'm trying to find. You're going to label them Z1 and Z2 maybe. And then I suggest what you do is you draw out your distribution. You draw it out and you say to yourself, okay, this is what the region that I'm given looks like. How can I convert that using symmetry to a region that I can find using the tables of data? And that means you're going to have to be flipping to get the reflection. And when you reflect, what you do is you replace your Z value with the equivalent negative Z value. And sometimes what you're going to have to do is, instead of calculating the value greater than, you're going to have to find the value less than, which means you've got to do 1 minus that region. Okay, so if you learn those tricks and practice them, hopefully it's okay. I think the real key thing is just draw out your diagram. If you draw out your diagram, you are much more likely to be able to get the right answer. Okay, hope that was helpful. All right, so here we are in question 5. The population of 150 villages in the UK to the nearest 100 are summarized in the table. We want to draw a histogram to represent this information. Well, the first thing is it's to the nearest 100. So really we should change these things to reflect that. So if population is the variable x, then what this means is that x is between 50 and 850. This one is 850 all the way up to 1,250. This one is 1,250 all the way up to 2,050. This one is 2,050 all the way up to 3,250. And this one here is 3,250 all the way up to 4,850. Okay, so just ever so slightly changed it. And I've been a little bit lazy there with the notation, but really what I should say is that x is greater than or equal to 50 and less than 850. That's what I mean by all these other values. Well, if I want to draw the histogram, then what I need to know the class width of each of these. I need to see how big this is. So I've got to do the top one, 850 minus the bottom one. If I do 850 minus 50, I get a class width of 800. And then 1250 minus 850 is a class width of 400. And 2050 minus 1250 is 800. This one here is 1200. And this one here is going to be 1600. Okay, so that's me getting all of the class widths. Well, now that I've got the class widths, what I want to find is the probability density. The probability density is found by taking each of these frequencies. Sorry, not probability density. I meant to say frequency density. Do beg your pardon. Frequency density is by taking each of these frequencies and dividing through by the class width. So we're going to get 8 divided by 800, okay, which is going to be 0.01. 0.01. I want to do 12 divided by 400, which is 0.03. Okay, and 50 divided by 800, okay, which is 1 upon 16, or 0.065. And 48 divided by 1200, which is 0.04. And 32 divided by 1600, so 32 divided by 1600, and that gives me 0.02. Okay, well, I want to represent this on a histogram. So let me just bring that up. And what can I say? I want to go from all the way up to basically 5,000, I suppose. So how would I draw this? Let me put this on that. I'll draw the axis there. And I'm going to make this 0, 1,000, 2,000, 3,000, 4,000, 5,000, and there's 6,000. We don't need to go that far. Okay, and what do we want? The biggest density is 0.0625. So if I was to draw that, take this thing here, I'm going to go up like that. Oh. And so I'm probably going to go up in increments of 0.01. So 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07. And I should probably label this as, this is my X, isn't it, here? Because I've already labeled it earlier, or it's population. And this thing here is the frequency density. Frequency density. Okay, then what do I want? From 50 to 850, I've got to have a frequency density of 0.01. Let's draw that on. So from 50 to 850. I'm going to do that. So 50 is there-ish. It's going to be a bit difficult to do this, guys, with kind of tablet I've got. So that's kind of roughly there. And then I want from 850 to 1250, 0.03. So 850 to 1250, sort of like that. And then from 1250 to 2050 is 0.0625. Up to 2050, isn't it? 0.0625. Sort of there, I guess. Up to 2050, like there. And then from 2050 to 3250 is 0.04. 3250, I guess, is like that-ish. And from 3250 to 4850 is 0.02. Up to 4850. 4,850, sorry, is what I meant to say. It's going to look something like that. So now I think basically I just got to join up these lines. Like that. That. Okay, mine are not going to be super accurate, guys, because I'm using a tablet and it's not going to be a little bit off, but hopefully that's the kind of idea that you get. Ah. That. Okay, and that will be my histogram. I'm just going to check it against the mark scheme, see if I'm basically in the right ballpark. Yeah, okay. So if I just check the mark scheme, it says all heights must be correct on the graph for 1 mark. The bar ends at 50, 850, 1250, 2050. Read at the axis with a horizontal linear scale with at least 3 values indicated. So you need to make sure that you've hit the right points on the x-axis, right? So it needs to be that plus or minus 50. Axis labeled frequency, density, and population, or equivalent in a title. Linear vertical scale with at least 3 values indicated. The vertical axis must cover at least the range 0 to 0.0625. Okay, so just label your axes, make sure everything's nice and clear, put numbers on it. So basically something that looks like this, and you want to make sure that the values here are basically the right ones. So this should be 850, for example. Okay, all right. Okay then, so parts B and C of this question, we want to write down the class interval which contains the median of this information. What's the idea of the median? Well, basically you put all of the items in order and you select the middle item. So in this case, what we've got is we've got 150 items of information. So we want to find the middle of that, the kind of the middle term. And the way we would do that is we take the 150 plus 1 divided by 2th term. Okay. And so if we do that, 151 divided by 2, 151 divided by 2, that's going to be the 75th term. It's kind of a bit odd to think about the 5th term, but never mind. In this case, it doesn't matter because we've got the 75th and 76th term are all going to be in the same category. So let's scroll up. Where's the 75th one going to be? Well, I think it's probably good to do a cumulative frequency. So this is 8. 8 plus 12 is 20. 20 plus 50 is 70. And then 70 plus 48 is going to be 118. And this one is going to be 150. So where is the 75th term going to be? Well, it's going to be somewhere in this group, the 2,100 to 3,200, or we could say it's in the 4th category. So let's put it as in the 2,100 to 3,200 group. Yep, or the 4th category, or 4th group. Okay, the next one, we want to find the greatest possible value of the interquartile range for the populations of the 150 villages. Well, how do we get the interquartile range? We basically get the lower quartile value and the upper quartile value. And we do the upper quartile minus the lower quartile. So we do upper quartile minus lower quartile. It's what we call the interquartile range. So how do we get the upper quartile and the lower quartile? Well, upper quartile is going to be equal to the 150 plus 1 3/4 term. I know it's a bit of an odd way of saying it, but basically I get all of my data, right? And I find the data point that is 3/4 of the way along the line. So with the median, I line up all my data and I find the one that's exactly halfway along the line. For the upper quartile, I find the one that's 3/4 of the way along the line. So if I do 151 times by 3/4, and what that's going to be is the 113.25th term. So the 113.25th term. Okay, so in what group is that going to be? Let's go up to here. The 113th, well, it's going to be in this group here, right? Because we can't be bigger than 118. We're going to be somewhere in here. Well, what's the biggest possible value that the upper quartile can take then? Well, it can go all the way up to 3,200 and almost 50, right? It can't be actually 50 because then we would be in this category here because we'd round up to 3,300. So the biggest value that we can take here is 3,249. So we want the biggest value, 3,249. We're just going to highlight that that's the biggest possible that it could be. All right, how do we get the lower quartile? Same thing, but this time we're going to take the quarter of 150 plus 1th term. And so if I do that, so 151 divided by 4, that is going to be the 37.75th term. That's the 37.75th term. And if I just go back up to my data, that's going to be somewhere in this category here. And I want to be on the lower end of that category. What's the lowest end I could be? I could be 1,250. If I'm 1,250, I will get rounded up to here. So the lowest value is 1,250. 1,250 being the smallest, because we want the biggest value for the upper and the smallest for the lower, because then if I do the upper minus lower, I'm going to get the biggest possible value. So the biggest interquartile range which is possible is going to be 3,249 minus 1,250. Okay, so 3,249 minus 1,250, and that is 1,999. So 1,999. Okay, I'm just going to check my answers, make sure that that's all right. Yep, that's okay. All right, here we are in question 6. Eli has 4 fair 4-sided dice. I'm going to try saying that early in the morning, with sides labels 1, 2, 3, 4. He throws all 4 dice at the same time. The random variable x denotes the number of 2s obtained. Show that the probability that x is equal to 3 is 3 upon 64. Well, basically what you need to understand is that this is a binomial expansion, a binomial distribution question, where what we've got is the probability of success, or what we define as success, is getting a 2. Okay, so in this case, the probability of getting a 2 is a quarter, and the probability of failure, which is 1 minus p, is therefore equal to 3/4. Well, how many trials do we have in this particular case? We've got 4 trials. Why is that? Well, because basically we can count each dice as being a trial. So if you throw all 4 at the same time, it's actually really the same thing as having one die and basically throwing it 4 times. So in this case, n is equal to 4. So what we can say, if we want to define this, is let x be the number of 2s, and that means that x is binomially distributed n comma p, which is 4 comma a quarter. Well then, how do we show that the probability that x is equal to 3? Well, the probability that x is equal to 3 is given by nc3, so 4c3, the probability of success, which is a quarter to the power of 3, times by the probability of failure, which is 3/4 to the power of 1, because it's got to be 4 minus 3 in this case. All right, then, so we're going to calculate 4c3, which I think is 4. 1 upon 4 cubed, so that's 1 upon 64. And 3 to the power of 4, so we get 3 there times by 4. And hopefully you recognize we don't really need a calculator for this, because the 4 is going to cancel off, chop, chop. And so we're left with 3 upon 64, which is our answer. Okay, so that's 3 upon 64. I don't think the math there is actually that difficult. The difficulty is actually being able to interpret the question correctly, to realize that this is a binomial question, and that these are the values that we need to use. Okay, so I think probably the trick here that will fool people is, oh, they're throwing the 4 dice at the same time. If it was to say to you, he threw the dice 1 time, 2 time, 3 time, 4 times, then I think more students would understand this is a binomial binomial distribution question. But basically, this is the same thing, right? Throwing them all at the same time is the same as taking one die, throwing it 4 times, right? Still 4 trials. Part B, want to complete the probability distribution table for x. Well, we've just got to do it 2 more times, right? So it's a little bit tedious, but never mind. Probability that x is equal to 1 is equal to 4c1, a quarter to the power of 1, 3 quarters to the power of 3. So if you do that, 4c1 is 4. We're going to get a quarter there, and 3 quarters to the power of 3. So 3 to the power of 3 is 27. 4 to the power of 3 is 64. So we're going to cancel off those 4s, chop, chop, and we're left with 27 upon 64. So we can put that in. 27 upon 64. Then what's the probability that x is equal to 2? It's just the same thing. 4c2, a quarter to the power of 2, times by 3 quarters to the power of 2. We just expand that out. So 4c2, what's 4c2? I think it's 6. Let me just check. Yeah, that's 6. Times by 1 upon 16. Times by 9 upon 16. I'm a little bit lazy at the moment, so I'm just going to use my calculator. So we got 16 squared on the bottom, and we're going to have 9 times by 6 divided by that is 27 upon 128. So 27 upon 128, so that's going to go there. All right, then. Part C, want to find the expectation of x. Well, the expectation of x for a discrete distribution is defined in the following way. It is the summation of each of the x values times by the probability of those corresponding x values. So what's that going to mean in this case? We go back up to our table of data. What we've got to do is we've got to do this times by this, plus 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 this times by this. And I encourage you to write it out very clearly for the sake of the examiner. So what you've got is the expectation of x is going to be equal to 0 times by 81 upon 256. So that's just 0, plus 1 times by 27 upon 64, plus 2 times by 27 upon 128. Well, that's 27 upon 64. Plus 3 times by 3 upon 64, that's 9 upon 64, and plus 4 upon 256, so 254, that's 1 upon 64. So I'm going to add up all these. I got 27 plus 27, plus 9, plus 1, that is 64 upon 64, and of course 64 upon 64 is just equal to 1. The expectation here of our distribution is 1. All right, so we're in the last part of this question. Eli throws the 4 dice at the same time on 96 occasions. Use an approximation to find the probability that he obtains at least 2 2s on fewer than 20 of these equations. Okay, so I've copied and pasted the table that we've had before, so we have all of the values. What this question is it is a normal approximation to the binomial distribution. So first what we want to do is want to find the probability that he obtains at least 2 2s. So let's write that down. The probability of at least 2 2s. And what's that going to be given by? Well, we've got to add up these values here, right? The probability that he gets a 2 or a 3 or a 4. So to do that, I'm just going to use my calculator. So 27 over 128 plus 3 over 64 plus 1 over 256. And what I'm going to get is 67 over 256. So this is 67 over 256. Well, then what we want to do is we want to find the different distribution, which I'm going to call y. So we're going to say let y be the number of times that the person gets at least 2 2s. And if this is the case, then we know that y can be approximated with a normal distribution, right, with some mean mu and some variance sigma squared. Well, how do we get the mean and how do we get the variance from this? Well, the approximation is the mean is equal to n times by p, the number of trials times by the probability of success. So we're going to have n is 96 times by our 67 upon 256. So 96 times by 67 upon 256. If I do that on my calculator, what I get is 25.125. And what's the variance equal to? The variance is equal to NPQ, where Q is the probability of failure. So it's going to be N times by P times by 1 minus P, if you prefer. And if I do that, if I put those values in, and multiply by 1 minus 67 divided by 256 there. And what I should get is 18.5493. So I'll write that down, 18.5493. And you can really keep going. I think in many ways it's helpful to have more decimal places for later on. So we are saying that in this case, y is normally distributed with a mean of 25.125 with a variance of 18.5493. Okay, now what are we being asked to find? I want to find the probability that he obtains at least 2 2s on fewer than 20 of these occasions, beg your pardon. So we want the probability that y is less than 20. Okay, now because what we've done is we've got a discrete approximation of we've got a continuous approximation of a discrete distribution, then we need to use the continuity correction, which means that what this thing really means is the probability that y is less than or equal to 19, right? So we can have 0, 1, 2, 3, 4, all the way up to 19. And so this means we've got to have the probability that y is less than or equal to 19.5. Okay, so we've got to round down because we want to be less than our 20. We don't want to round up, because if we went up to 20.5, for example, then what that would mean is that we would also be including the value of 20, right? Sort of like this. You got a line 19, 20, 21. We want to be less than 20. So it's kind of like we want to be all the way up to there, right? Because we want to be less than it, so we want to be on the left-hand side of it. Okay, well then in order to do this, we need to use our Z transformation. So we're finding the probability that Z is less than or equal to our 19.5 minus our mean, 25.125, all over our sigma. And we need to remember to square root that. So we've got 18.5493 square rooted. So if I do this, what am I going to get? 19.5 minus the 25.125 divided by the square root of the 18.5493. So let's do that. Okay, then what I get is we're finding the probability that Z is less than or equal to negative 1.3060. Okay, now we need to remember what the how to interpret the Z distribution. I think the best way to do that is just to draw a graph. We want to draw out what the Z distribution looks like. Now remember, the Z distribution is symmetrical about 0. Right, so here's 0. Our graph is going to look something like this. Or our distribution is going to look something like this, rather. Oh dear. And we want to find the probability that we are less than negative 1.3060. So let's say that's here. That's negative 1.3060. So we're being asked to find this particular region, so this region here. But unfortunately, the graph doesn't, the table of data rather, doesn't allow us to find that region because it doesn't have negative values of Z. But what it does have is it has positive values of Z. So we can use the principle of symmetry and say we've got 1.3060 here and say that this probability is the same there. Right, so in other words, because this region here is the same area as this region here, the probability that Z is less than negative 1.3060 is the same as the probability that Z is greater than positive 1.3060. So let's write that. This is the probability that Z is greater than 1.3060. Okay, well, again, the tables don't tell us the probability of being greater than a certain value. They tell us the probability of being less than. So what can we do? Well, if we imagine this region here, which I'll shade in red, right? That's the probability that I'm less than 1.3060. And that's going to be the same thing as 1 minus. Right, so this is 1 minus probability that Z is less than 1.3060, right? Because if you think about it, what we're saying is this area here, the area in red, plus this area here, the area in green, must sum up to give 1, because the area underneath the whole distribution must be 1. So we can calculate this thing from our table of data. So we want to find 1.306, beg your pardon. So let's try to find that table of data. Where is that? 1.306. So let's go down. So we got 1.3 is there, 1.30, which is that one. So we just highlight that. 1.30, and 1.306 is this thing here, that thing there, right? Because I just scroll up so that you can see, right? So this is our adding 6. So 1.306 means that what we've got here is a probability value rather of 0.9032 plus the 0.0010, and that's going to combine to give a probability of 0.9042. Okay, so we're going to go over back to our working. Ooh. So that is over here. 1 minus 0.9042. And if I do that, 1 minus 0.9042, then what I should get is 0.0958. And that should be my answer. I'm just going to quickly check the mark scheme, make sure, because sometimes you can easily make a mistake. So where are we up to? 0.0958. Okay, so yeah, so that's the right answer. Okay, guys, so I'm hoping that this is proving helpful to you. Remember, if you are finding this helpful, please do like, please do subscribe. Take care. Okay, here we've got question 7. A child's wildlife magazine is published every Monday. For the next 12 weeks, it will include a model animal as free gift. There are 5 different models: tiger, leopard, rhinoceros, elephant, and buffalo, each with the same probability of being included. He buys 1 copy of the magazine every Monday. Find the probability that the first time that the free gift is an elephant is before the 6th Monday. Now, you can think about this, if you like, as being a geometric distribution. X is distributed geometrically a fifth. And what we're trying to find is the probability that X is less than 6. It's got to be before the 6th Monday. And that's the same thing as the probability that X is less than or equal to 5. And you can do that by adding up the probability X is equal to 0, X is equal to 1, X is equal to 2, X equals 3, all the way up to X is equal to 5. But the easiest way, I think, to think this through is just to draw it out, actually. So if we think about this, the outcomes could be as follow. He gets an elephant or he doesn't get an elephant in the first week. He gets an elephant or doesn't get an elephant in the second week. The third week, the same thing. 4th week, the same thing. And finally, the 5th week, the same thing. Now, in each of these situations, apart from one, he gets an elephant, right? He gets an elephant there, 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 and there. But in this outcome, he doesn't get an elephant at all. Well, what's the probability of not getting an elephant? It's going to be 4/5. So he's got to have 4/5 5 times. So that's going to be 4/5 to the power of 5. And then what's got to happen is he's got to be 1 minus that, right? Because we don't want that thing to happen. We want him to get an elephant at least once. We're going to do 4/5 to the power of 5. And we're going to do 1 minus that, which gives us 0.67232. And I think you need to round it up to 3 significant figures. So that's 0.672. Okay, so that's the answer to part A. Let's do part B. Find the probability that Sahim will get more than 2 leopards in the 12 magazines. Okay, so we can think of this as a binomial distribution. So let's think about this. Y is distributed binomially. He's got 12 different trials, right? Because he's getting the magazine on 12 separate occasions. And the probability of getting a leopard is a fifth. I should probably be a little bit more precise here. I should say something like let Y be the number of leopards in this case. Right, so I should really state what my distribution is. Okay, so what I want to do is I want to find the probability that Y is greater than 2. So that's the probability that Y is 3, 4, 5, 6, 7, 8, and all the way up to 12. But that's going to be a bit boring to do. So one, I think instead about doing 1 minus the probability that Y is less than or equal to 2. And the probability that Y is less than or equal to 2 is the same thing as the probability that Y is equal to 0, and the probability that Y is equal to 1, and the probability that Y is equal to 2. Okay, and in order to get these, I just got to do my binomial expansions rightly. So this will be 1 minus probability that Y is equal to 0. That's 12C0, a fifth to the power of 0, 4 fifths to the power of 12, plus 12C1, a fifth to the power of 1, 4 fifths to the power of 11, plus 12C2, a fifth to the power of 2, 4 fifths to the power of 10. Okay, so I just got to work all of that out now. So 12C0 is 1, a fifth to the power of 0 is 1, so we've got 4 upon 5 to the power of 12, so 4 upon 5 to the power of 12, whatever that is, plus 12C1 times by a fifth, and then times by 4 fifths to the power of 11. Okay, and that. And then plus 12C2, a fifth to the power of 2, times by 4 fifths to the power of 10. And I do that, equals. I want to do 1 minus that. Okay, and that gives me 0.44165. I'm just going to check if that's the answer. So I check against the mark scheme. 0.442. Yeah, so if I round it up, the three significant figures, 0.442. Okay, so that's the way you got to do it. You need to recognize that this is a binomial distribution, and you need to go through your binomial expansions properly. Okay. Okay then, so last question of this paper, we want to find the probability that after 5 weeks, Sahim has exactly one of each animal. Now, the way I think about this is a little bit different to the mark scheme. What we're really saying is the outcome we want is we've got the tiger, the leopard, the rhino, the elephant, and the buffalo, but we don't care about which order we have this in, right? We could have leopard, rhino, elephant, tiger, buffalo, whatever. So what this is about here is about how many ways can we rearrange these particular letters? And we know the number of ways in which we can rearrange these letters is going to be equal to 5 factorial, right? We learned that hopefully fairly early on in the course. All right then, well, what is the total number of all possible outcomes over the course of the 5 weeks? I can imagine it's sort of like this, right? 1, 2, 3, 4, 5. What could happen on the first week? Well, on the first week, I could get any one of these 5 options, right? So there are 5 options here. And the same is true for the second week, right? There are also 5 options for that. And the same is true for the third week, and for the fourth week, and the fifth week. So the total number of ways possible is actually 5 times by 5 times by 5 times by 5 times by 5, or in other words, 5 to the power of 5. So the total number of ways in which I could get the animals is given by this thing here. That's all possible outcomes. And this 5 factorial here represents the number of outcomes where I get one of each animal. So therefore, the probability in the end, we can say the probability that we're interested in is 5 factorial divided by 5 to the power of 5. And if I key that into a calculator, 5 factorial divided by 5 to the power of 5, then what I get is 24 over 625, which I believe is the answer. So that's not the answer they give you in the mark scheme, but I think that's probably a pretty neat way of looking at it, or it is at least to me. Okay, one of the ways in which they do it is they basically take the probability of choosing any particular animal, which is 0.2, and you have that to the power of 5 because you got it 5 times. And then what they do is they multiply it by 5 factorial because it's the number of different ways in which you can arrange it. Okay. All right, guys, I hope this was helpful. If you're finding these videos useful, please do like, please do subscribe, and leave comments as well if there are things that confuse you or things that could be done better. I'd love to help you more. Take care. Good luck with your studies.